Подожди, что ты говоришь? Стой, остановись.
Partial technology is the science that deals with the management of geographic information using information communication and technology. So what is management? Management is all acquisition, capture, modeling, processing, storage, retrieval, analysis. So any operation you have to make to this data is made with geomatics. Second is the geomatic techniques. You are archaeologists, most of you, but when we talk in geomatics, we used to separate depending on the object of the size. There is one methodology better than another. So when we work in caves, we try to separate three scenarios. The first one in gray, that are the rock art panels and biodeterioration zones that are usually around 1 square meter or 2, 3, 5, 10 at the most square meters. The second is the site, the cave, and all the caves surrounding the cave that are around 100 meters, 500, less than kilometer, but around that extension. And the third are the protective environment and the context. So in this context, we used to say that one technique is more efficient than another. So usually when we work in panels or in small areas, we use photogrammetry, macrophotogrammetry, microscope copy, and sometimes laser scanner. But when we are working inside documentation or in cave documentation, we used to use a 3D terrestrial laser scanner, total station, I will show later. The exterior with drone, with unmanned aerial vehicle, and all the protective environment with remote sensing, satellite remote sensing, aerial imagery. It depends on the scale. So this is how we measure what you see, but there are two techniques that we use to integrate with all this that serves to document what you cannot see. One is the overlying thickness we will see later with GPR, and the other is the art of the biodeterioration with multispectral or hyperspectral remote sensing. So this is the chart we manage to see what is the most efficient technique depending on the object size and the accuracy you need to reach. I'm going to show you some examples. But first of all, I would like to introduce caves. I don't know if you are used to working caves, but basically a cave is a natural underground void large enough for human access, formed by geological processes such as dissolution, erosion, even tectonic activity, and characterized by a stable microenvironment that can preserve geological, biological, cultural records over a long period of time. So this is how a cave is formed, and caves or speleology and geomatics are has a long time has been always be in relation because the importance lying in geomatics is to put what all the observations that is caves of cave parameters. I mean, traditionally, the aim of cave surveying was to produce a floor plan, longitudinal profile, cross sections, and this information was used to put geological data, geomorphological data, all the archaeological evidence, even some climate measurement, biological information, fauna, wildlife. You know, the purpose of geomatics and the plans was to create a frame in which to put all the information we have from the cave. And now, when you are working in cultural heritage cave, you have to work following these principles. You cannot afford to take information only for dissemination or research. So once you take one picture or you scan the site, this information has to be used for research, management, and dissemination. So you have to be very efficient when you work. And what is the reality of a cave and the rock art? So when you are working in cave with heritage or cultural heritage, usually you are working in a card system. In this card system, you have some biotic elements like microorganisms, flora, fauna, and even human beings, and some other abiotic elements. Abiotic elements is what is not biotic, so not living. You have the rock, you have the climate, the climatology, the water, the fire, and a small amount of caves has art pigment. This is very important because here in Cantabria, it's 1%, 2% of the caves have some art, but the most of the caves don't have art. So this is the reality of what you have when you work in caves. You have to respect living things and non-living things. Okay? So just to finish the introduction, I want to think that, okay, we have a cave, we have art in cave, or we have some remainings. So we have to store this in a repository. So in the last 5 years, 6 years, we have developed a digital twin of caves. We have stored in 10 dimensions. I think it's a bit messy, but I'm going to talk about any of these dimensions and how Geomatics fulfills all these boxes. So quickly, the first dimension is all the old non-metric information. You know, all literal description, sketches, artifacts inventories, excavation diaries. You know, all this information, usually very old, we put in the first dimension. The second dimension are planimetry. You know, plans, longitudinal transverse, all the information you have, independent of the accuracy, because accuracy we will talk about that later. But any information you can, with dimensions of the cave, you should store in the 2D. 3D are the way all the information about the current conditions. Here we store all the information taken from 3D terrestrial laser scanner, GPR, photogrammetry, microphotogrammetry, remote sensing. I will show you later some examples. 4 dimension is for time, the evolution. So in this living laboratory we have, that is a cave, how climate varies, how the water moves, how the biodeterioration varies, and the humidity, if you have some conservation issues dealing with that. The fifth dimension is about parallels. Okay, we have the current model of the cave, but this cave, when was discovered, was different. In Paleolithic or Neolithic time was different. So you can manage 3, 4, 5 parallels. Even you can include future scenarios if you know what work you are going to make. The sixth dimension is estimation, estimates. So what if, or what happens if we made this or that, if we put people in the cave, if we remove, you know, all the infrastructure, or we put some infrastructure. So that kind of questions, because the seventh dimension is aimed to talk about sustainability of the cave, or when and how a cave is sustainable, or rock art is not getting worse. Okay, so can I afford to let people come into the cave, or has the cave to be closed? So that sort of questions. Eighth dimension deal with maintenance. All the things that is not original from the cave is put in a database, and all the things you have to change, one light, a seismograph or a door, or it's included in this database. The ninth dimension is security and all the safety analysis, emergency response plans, fire safety, all the evacuation plans. It is exclusively from security. And the last dimension is the relation of the cave with the environment and all the surrounding places now and in the past. So these are the boxes we use to store all data from the cave. So we are going to start, okay, from the beginning till the end. So first dimension, as I said, is non-metric document. So this is, sorry, it's in Spanish, but this is the type of information we use to store. Just descriptions of elements of the cave that were taken maybe in 20s, 30s, 40s of the last century. There are different ways to document caves. So first interaction was the description of the cavity. The second were the sketches without the scale, just drawings. The third were drawings at a glance, made without instruments, but an approximate scale. And later, the accuracy was improved, including rudimentary plans with compass, low accuracy compass. So along the history, because we have been integrating data from 1860, so 150 years ago, the accuracy and all the documentation of the cave has varied. So in this plan, plan plane was made in 1920. You see the shape of the cave, El Castillo Cave. And this is 60 years later, the speleologic plant of the cave. So as you can see, the shapes are almost the same, and maybe you can use in local part, but not to have the whole cave. So non-metric information of caves are thus rudimentary plans. The same happened with you when the art was being documented. First, the art was documented by description. Here you see a notebook from 1940 of El Castillo Cave. Later, hand drawing. You see a Ave Braille with these works of putting the candles in the cave. Direct tracings with acetate put on the art and just draw with direct tracings. Later, the frottage. It was a way of documenting art, but all these methods deteriorate the art. So, and the molds, even when there were engravements. And later, in 60s, arose the analog photography with visible light, infrared light, ultraviolet light. 60s, 70s, 80s, it was the moment. 50s even. There are some pictures taken in 50s in Altamira. The first picture taken in Altamira was in 20s, but it has disappeared. Later in 1990s were the digital imaging, color, RGB or multiband cameras. And now when it's very common to find, enhancement technique, the stretch, it's a software that creates the correlation to enhance the pigments. And the latest is the multispectral and hyperspectral analysis method that I will talk later. So this has been how in the last 150 years, the documentation of the art of the case has varied, okay? These are some examples of field notebooks of El Castillo Cave, Monedas Cave, the drawings they made in the field, the the drawings they make in the office. This is the draft. This is the final composition of the drawing of a bison. This is a bison in El Castillo cave. And all this documentation has to be preserved and now has a historical importance that we cannot remove. We should include, we have to keep, and we even has to compare. Okay, here the same happens with pictures. Okay, if you have pictures, very old pictures of these places, for instance, this is el Monte Castillo, the place where we have 5 World Heritage Places in 1910s, in 1923, and recently, 24, 9, 13, 18, and now. So as you can see, this is about the same place of the mount, but you can see here that in the last 20 years, the vegetation on the mount has changed. So this is very important for conservation, okay? Because this highest amount of vegetation has made some problems in the cave arise because now it's more dry and we have problems, new problems that we didn't have in 20 years ago or with more people visiting the cave. And more historic information. This is a photo mosaic taken of the polychrome sailing of Altamira in 1978. This was a collection of pictures like this that you can recover and reprocess and to analyze with current technology. So all this information is very useful. Principally, if you work in an open or a living laboratory, you need to know how was the cave yesterday or 10, 15, 100 years ago. So any picture that initially can be useless, you can reprocess with current methods to take advantage and to control all changes in the cave. Here we have detection changes in these 50 years, almost 50 years. So it's very important, all the historical information and to process with the current technologies. Okay, so after this first dimension, the second dimension is planimetry. Planimetry is basically plan planes, traverse, with traditional methods, total station, and later with 3D terrestrial laser scanner. If accuracy is very important, you can use some microgeodetic networks, polygonal, traverse, radiations. So way of measuring caves and underground sites has varied as well in the last years. I'm going to show you an example. This is the plan plane of the first sketch of Altamira. Around is we don't know exactly the date, but around at the end of the 19th century. Okay, this is the first sketch was made before the paintings were discovered. They knew the cave, but not the pictures. Later, when the paintings were discovered in the newspaper, appeared a second plane. You can see here in the right side and down, a sketch of the pictures. This is 1880. This was in 1881 the first map the Arle made of the cave and the first section, and this what he used to put where things happen. Later, in 1924, Corral, it was a Spanish engineer, made this plan. This plan is quite close to the current situation. And he made, traverse sections, several engineer. He made an engineer project as well. This is the plan plane appears in the publication of the art with Henry Braille, Hugo Vermayer. This plan plane is 1935. In 42 there is another plan plane that some parts lags. This is in 1975, with total station or tachymeter, more than total station. This is 1998 plan plane and that. Okay, I have a new one, but I didn't put because I will show you later. So all the planimetry has changed. So you have to take advantage of all this information because it's useful, because someone somewhere has represented what happened in several places. So to take advantage of all this information, it's very important to know how was the cave in that moment. Here you have the first plan plane of El Castillo cave and the current plan plane. And even if you use the 1980s, 86 speleologic plan, you see that the general shapes maybe is not very accurate, but if you fit it locally, you can uh, use it like to integrate that information in your good model. So what was the scope of this 3D? To create an accurate map for the whole cave, How? With topography. You have a traverse through the cave. If accuracy is very important, you can create a microgeodetic network. This network was made with the scan positions. You measure spheres, and these spheres serve like a trilateration edge of a microgeodetic network. And this why? Because today, all the softwares automatically fits most of point clouds, but this is the only way to have uncertainty of each part of the cave, okay? To create this information, plans, traverse sections with exterior soil, longitudinal sections, to put the exterior in cartography over the cave, just to know what happens in the exterior and in the interior. But you can create as well these 3D current maps. The first is the ground level maps, the height of the ground, the height of the roof or roof dimension map. And once you have these two values, you can calculate the height gallery map, that is the distance between the soil and the roof of the cave. And you can calculate the overlaying layer thickness, that is the distance between the roof and the exterior. This is very important for conservation, to have this overlying layer thickness, to see if the cave is 5, 10 meters or 100 meters from the exterior, just to see if you have some gases interchange, water interchange, and that sort of information. So if you compare this, you see this is left the speleologic map, right, the 3D terrestrial laser scanner map. Here, I hope you see the cursor. Look, this is El Lago Cave here, and this is El Lago Cave. So, speleologic maps, this speleologic map was slightly incomplete here. And look, this part are separated, but we realize this part are almost touching. So when you integrate all this information, I think it's better here to see it, or even here. Look, this when you put accurate 3D information all together, you see with highest accuracy the relationship between all these voids in the mountain, all these caves. And here you discover that apparently these caves were very separate, and now are almost touching. There is around 3-4 meters of distance between these 2 points. So we discovered that this cave is Chimeneas Cave, that is a World Heritage place, is about 4 meters from 2 other caves. In some of them could be interchange, gases interchange, and all these problems that could come from it. This is another example. This is a mountain and the karst of the mountain. These are the caves. There are 9 caves. And when you put all them together, you see the relationship between them. Okay, this is Bitarte in Basque Country. And I'm not going to show you the whole video because it's just to show all the caves, but this is the 3rd cave. And you can see the relationship with the surrounding caves. This is how it's in the outside. Okay, so this is the current condition of the cave. These models are created by laser scanner, but you can also create this model with photogrammetry. What the advantage of the photogrammetry? That you have texture and you have, if you calibrate color, you have color calibrate and you can compare what you have in front. Here you have only geometry and a digital number of the laser scanner that, depending on the wavelength, that usually is lost. Okay, you keep it in point clouds but not in models because it's useless. Okay, you could use, but it's not common to keep it. So here you have all the relationship, but imagine that you need texture of this cave. So you can create photogrammetry. This is photogrammetry, okay? So this photogrammetry is 2 millimeters pixel size, and we create this for a virtual reality scenario to show the cave, okay? So, and to document the art. So I'm not going to show the full video, but you have an idea. This is one cave, this is another cave. You have all the infrastructure that we are going to put later in the digital twin, okay? And this is the sites, the excavations, and you can move through a video, through a virtual reality, the method you prefer, okay? And here is the way to, these caves are close to the people, and this is the only way to visit the cave with these parts. So we are dealing with geometry. We have laser scanner geometry, we have a photogrammetry geometry, but if we need to know about the overlying thickness, we should integrate a GPR. GPR tells you how the overlying layer is. So if the overlying is the layers that are between the roof and the exterior, okay? So usually caves has suffered a long time dissolution processes, and this dissolution maybe has broken, the overlying thickness. So the only way to see the fractures, if there is a line, if there are detachment joints, all these geological processes, is by integration GPR. GPR usually is not easy to integrate in a 3D model. This is a 3D of GPR, the left, with a normal standard GPR instrument. This is an interpolation of that information in 2D in a GIS. This is one radargram just to show all the fractures and the direction of the sailing. And this is the humidity, where the humidity is stored. This is Altamira Cave. And here, humidity is very important because the water is cleaning the pigment, okay? And it's moving the pigment and makes it to fall to the soil. So I will show you later in more detail, but this is what a GPR usually, or you can make with a GPR. Okay, if you take this information and put in 3D, you can create 3D models and to integrate with the UAV exterior model with the 3D terrestrial laser scanner cave model. And this brown information are the main fractures of the cave, where is broken. And here you can see here in the middle, in here, a very long this fracture. And this is very important because it talks about the stability of the overlying things, okay? So this is 3D, release scanner, photogrammetry, GPR. So we are documenting the cave, but if we are documenting art, usually we take pictures. So when you take a picture, you are recording 3 bands, one red band, one green band, and one blue band. A long time ago, people start using near infrared films or ultraviolet films. What they made was to use 4 bands, one ultraviolet or one near infrared or 5 bands, and they usually improve the results of the drawings because there are some information that is not visible to the eye that is stored in this part of the spectra. Here, you have wavelengths, okay? These are wavelength and reflectivity. Don't be afraid. Okay, just tell you, from 400 until 700, 750 is what the eye can see, okay? We usually see a 450 nanometers wavelength for the blue color, 550 for the green color, and around 660 for the red color, okay? So if you take the picture, you have only 3 slices of this continuous spectra. Okay, so in rock art, there are some processes that sometimes are not cannot be seen to the eye, and you need to go to other parts of the spectra to see or to separate them. Here, if you have these four signals, you can separate or hear better or here than in here. That is almost impossible because they coincide. So these are the basics of hyperspectral, multispectral remote sensing. If you have multispectral, you can use some filters in the wavelengths of interest to record this data and to see or try to separate these classes, okay? If you have other types of multispectral sensor, I will show you now. You can have a continuous from 380 till 1000 nanometers of bands. You have almost 600, 20 nanometers band, 30 bands of 20 nanometers. Hyperspectral remote sensing is basically the same, but instead of have tens of bands, you have hundreds of bands, okay? In the part of the region of the spectra you see that can be of interest. So here, I'm going to show you, look, this is the camera is here. This was a Musis camera with 28 bands between 370 and 1000. This is a Specking Q. This is a current camera that you can have. This is a filter wheel camera, and this is a hyperspectral sensor. You can have up to 204 bands between 400 and 1000 nanometers. Okay, this is a compact camera, and this is the industrial version. Okay, it's more accurate, it's better, but it's more heavy and bigger. Okay, but always working in the visible spectra. Okay, not the visible, but visible and near infrared and the threshold of the ultraviolet. So if you want or you need to work in other region, you could use cameras that work beyond the visible spectra. This is a camera working between 900 and 1700 or even 2000 and 5000 nanometers. This is a filter wheel cool camera. Okay, this is a prototype. And basically, what you try to get is what you cannot see or the stretch cannot give you. Okay, I'm going to show you some examples. Okay, when you work here, you can see that the setup is very big. So it's not very compact because you need a white pattern here, you need your laptop, you need lights, and you need this. This is very important when you work in heritage, that if you are lighting, you have to make sure that you are not hitting the rock. So you need thermography. First, you need lights, you need to calibrate lights, you have to make sure that you are lighting the part of the spectra you need to measure. So, for instance, this is the spectra of a LED near infrared camera. This is the typical night vision camera, you know, for security is this. These LEDs only illuminate 800 around 850 nanometers, so you cannot appreciate you are being illuminated. Okay, this is a continuous light, the black one. Okay, this is a photolita, and these are the typical kitchen tubes. Okay, and this green at the end is the ultraviolet LED, the typical light in the discos, you know, for looking on the white things. So each light emits heat, okay, and hits the surface, and you need to control this with the thermography to make sure that no more than 0.1, because you can reach the deep points and to start making problems in the cave. I will help later. So this is one example. This is what you see when you apply remote sensing. These people appears, okay, that are very difficult or almost impossible to see, okay. This is a place we went here to document this. Okay, this is a man, an anchor man, and what we found was this. This is what you see, and this is the thing appear. You know, this was a dance scene with women, suns, spirals, and all that. Okay, so it's very grateful because you can separate, okay, the visible from other parts of the spectra to show, you know, the figure. In Altamira, this is hyperspectral. So we saw is some lines that are below the art you can see. Okay. Here you can see in black these parallel lines that crosses all the sailing. So these are the first part of the sail that was painted. And here, this is one famous bison. You will see a claviform here. This claviform is below, is older than the bison. But when they painted the bison, they respect the claviform symbol. So thanks to the hyperspectral remote sensing, we can isolate this signal and to document how was this claviform, okay? Through the remote sensing techniques. This is the black pigment of the bison. This is another different ochre pigment in the front of the bison. So here you can separate colors, okay? And what is this useful for here? This is what you see, and when you apply remote sensing, suddenly, you know, the one deer appears like this. And you can create a image combination just to document it. And what is useful? Okay, you have the 3D model, you have a photogrammetric 3D model, and where you need to integrate the hyperspectral remote sensing analysis to the 3D model to create an stratigraphy of the art. Okay, this is el panel de las manos in El Castillo Cave. This is the oldest painted. Later, these animals were painted. Later, after these animals, these green animals, these black animals were painted. These are not visible to RGB camera because the stretch cannot give you any information about that. And this is the second phase of hands. Okay, usually here a debate was if the hands were up or below the orange animals. with remote sensing and archaeological prospection and studies, you can create this stratigraphy of this sailing of this panel of El Castillo cave. You have to think that between the first and the last, almost 30,000 years, more than 35,000 years pass. So the first hands are almost 38, 40,000 BP. Okay, and the last are Neolithic, and so you have a very wide, and this is the superposition of all these stages in different colors, just to understand how this picture was made. Okay, so now you have all this information, but the only way to separate and to see what was made before and after is by doing this. So this is augmented reality in a 3D model, digital 3D model. But you can create this of art, but you can also create these parallels, because these are parallels. When in Gravitian, how was the cave in that date and that date? So you can activate only that layer. The same, you can make the same in the cave, okay? I will show you later. Because the 4th dimension, okay, we finished. This is not 5D, it's 3D, but as well 3D, 5D, sorry. The 4th dimension, after documenting all the 3 dimensions, with terrestrial laser scanner, microgeodetic networks, UAV, photogrammetry, high resolution photogrammetry, for rock art, hyperspectral remote sensing for rock art, and GPR for the overlying thickness. The 4th dimension are the evolution of things. So the first thing you have to control is weather, the climate, okay? You have to control temperatures, CU2, radon, all the parameters. These are just sensors that are in the cave and generate a database, okay? But you have to document all the deterioration processes as well. Here you can see, this is Altamira. Look, these are parts of pigments that appear in 2015, but sometimes later disappear. Okay, they fall to the floor, and you has to be able to measure that. Okay, all these differences. Here you see more differences. So to create a method to control the evolution of the deterioration is very important here. So the only way, or the way we made it, is by doing a 30 to 40 microns resolution photogrammetry, because it's the resolution you need to control these submillimeters pigment falling, okay? Another thing you have to control, a part of this, look, this is one symbol. This is the gap of the pigment gap. After, this is like a lagoon, it's the pigment on the surroundings is moved by water here, and when you have enough weight, it falls and creates a big laguna. And again, this process is repeated in several years. So the area is charged by pigment, and when you have a lot of weight, it falls and it starts be charged as well. So the pigment in the surroundings is moving to this area, and when it falls, the process is continually repeated. And with this method, you can calculate how many square millimeters the gap, this vault in the roof. You can monitor the process and to see and to assess the evolution, and now we are start taking conservation measurements just to prevent or try to move this water is moving the pigment, okay? This is the square millimeters area without pigment in different moments in different years. Okay, from 2013 till now. So in this moment is when the pigment fall, and now it's going down, 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 and once it reaches the maximum, will fall again. The same, not only the deterioration of art, also the biodeterioration. You know, all the abiotic parts I talked at the beginning, all the living things, you has to be controlled. Okay, you have here, these are very high resolution. The resolution of the picture is around 10 microns, GSD, sample size, grid size, sorry, pixel size, okay, 10 microns. And this is the detail. The resolution of this picture is around 1-2 micron per pixel, but it's not an ortho image. So it's about, 500,000 pixels by a square millimeter. So it's very high. This is a very small deterioration happens in a picture. Okay, it's an Aragon information that it's throwing the pigment out of the wall. And you can control living things, you can control unliving things, but you have to control water. So in Altamira, we have a very particular case, that is, we have a roof. The roof has these shapes, these deformations, and we have the problem that water comes from the outside through the overlying thickness layer, and it appears in the fractures of the ceiling. So what we made was to model how the water move by surface tension, through the ceiling. And we calculate the points, you can see them in black. You can see it in black, in dark blue. We modeled that, and the idea was to model like rivers. The water appears in a fracture and it moves till the lower part, and then it falls to the soil. This movement is no gravity, it's just surface tension. So it's water moving through the ceiling, not through the floor, because this is a ceiling, a roof in the cave. So the points we calculate with the 3D model were very close to, or coincide with, the gaps or the bulges of the paintings. So now, if there is a gap, it's an active place. So now we are starting working in the future active places. Okay, here you see, if you have still pigment, it's because this area has not been activated. So this is, a preventive conservation tool, just to see which are the active areas and which are going to be the following. Okay, this is the way we try to model it and to calculate and now we are starting taking some preventive conservation strategies in this area. Putting silicon wires just to deviate the water and all this. What we are doing the last 5 years, just to control humidity in these parts. Okay, we have a problem, that is that water falls, pigments, moves biodeterioration. So we need to know how water is stored in the overlying thickness in the first 40 centimeters. Just to see if there is water, now in several months, this water will fall and appear in the ceiling and move the pigment or the biodeterioration. So through GPR, we have modeled this. These are the slices. Look, this is the main fracture of the cave, this part. and the blue are the areas with highest humidity. And here, this is the area closest to the surface. You can see a big lagoon or a big area or an area with high humidity, and superpose the watersheds and the points where it's supposed to fall that water. So depending on the fracture of this water appears, it will flow into one point, one drop point or another drop point. So this is what we are doing to monitor the humidity in the roof of Altamira, just to prevent pigment to fall to the soil. Here you can see, instead of the first 450 centimeters, you need to control all. You have to use an antenna, GPR antenna of different frequency. Instead of 1,600 gig or megahertz, you can use 800 or 400 to go deeper and to see the fractures. This is all the fractures that they are a bit exaggerated, but these are the fractures that the sailing of Altamira has, cross-correlated with the geologic layer it has. So as you can see here, the level of fracturation in Altamira is very high. It's the same as when you take cookies and you break and you keep. So if they don't move, it's okay, but when you move, the stuff falls, small pieces of cookies. So here the case is the same. So with this application, we try to demonstrate the level of fracturation, but once we had the level of fracturation, we were interested to know where the water was stored through the depth of the sailing. Here, I'm going to show you, it's almost finished the fracturation. This is the water. This is the humidity stored in the sailing. So if you go down, this is 1 square meter because it's a detailed analysis. But we know that this water is stored in the main fracture of the cave, that are the borders, and in the interior area, in some lagoons that goes down through this fracture network. Okay. There are some parts that are drier than some others, but this is very interesting because all the relationship between all these layers. Okay, this is for preventive conservation. Okay, this is the problem. The water that is very close to the sailing, because in several months it will appear down by gravity. Okay. So I showed you how to manage climate, how to track or to monitor biodeterioration, the deterioration, and water. So all this information is very useful for preventive conservation. But you can have the current model, but you can also develop some historical model. For instance, this is the current model of Altamira and the model of Altamira when it was discovered, when the paintings were discovered. So here you can see that on the right, all the anthropic, all the works made by humans to preserve the caves and the original shape of the cave. So these are two models, but if you have, this is the exterior, the entrance in Paleolithic, and the entrance now. Now there is a door. In the Paleolithic was a very wide area. This is the level. Now the door is up of the original level, but you have all the excavation and all that. We have taken all the height from that, and this This is an artificial wall made to preserve the cave, just to prevent the cave from falling, from collapsing, yeah, to become alkaline. This wall was made in the 1930s, 40s, 1940s. Okay, so here you can understand the difference and to think that the cave you are visiting is not the same that was in the Paleolithic. Okay, so this has been made with the 3D laser scanner model, but you can also create these models to ambient this. This is Cova de la Sendra, how it was, how it's currently, and how it was in three historical moments. One, when they put goats, they keep goats in the cave. The second, when it was used to smoke food. That is the name of the cave is of that moment. And the third, that is 14,000 BP, how it was when people live in the cave. So you are doing the same track and you are looking the differences. Okay, this is the current photogrammetric model and the recreation of these three historical moments, just to understand all the excavation information, just to understand this layer corresponds to this, or the goats are here, and this is the level, and the living and all that. So these are the parallels. We can use these parallels just to show people, but you can calculate as well there. So it's very common now to estimate in current models. What we estimate? The effect of people visiting the cave. So this is the set dimension of the cave, okay? Look, this is the 3D model, and when you put people, they create an anomaly in the cave. You have to think that the cave is a very stable environment that is this stability has made the paintings to be preserved. And when you put one person, what you are doing is to put hot in the cave. Usually here the caves are between 9 and 14 degrees in this part of Spain. In some other higher temperature. And if one people comes into the cave, it is like a torch of 35, 36 degrees. So it creates, some air circulation flows that can be modeled just to see. Here you see the model, the 3D model, just to see how much time does the cave need to recover from that excitement. And these are estimations, but from historical data. Okay, this is the same cave I showed you before, la Cova de la Sendra, in two different moments that the outsides were different because of the difference in the sea level in this area. And in the right part, you can see some agriculture. They wanted to tell that some agriculture and people living and use the cave. And this is the storytelling of these models, okay? Just to see the difference between one scenario and the other. So if we keep, we will find the seventh dimension, that is sustainability. Basically, this is an analysis of all the data you have now, because this is always open to more data, to try to understand when the cave is sustainable or no, and to find the optimal conditions. For instance, here in Altamira, it's not the same a 5 people visit in summer than in winter. In summer, the cave needs 1 day to recover the effect of these 5 people. In winter, in a few hours, the cave has recovered. So is not always the same. It depends on the day and the exterior and interior conditions of the cave. So it depends on how isolated it's from the exterior and many other parameters. So all the information is useful, and you need what you need to make is the game sustainable. Just not put too much time in stress. Okay, when the cave is in stress, that monitor how many time needs to relax and to reach the original parameters. Okay, the eighth dimension is maintenance. All the parts that are from the cave, cables, seismographs, lights, data loggers are stored in a database to create an as-is model. So here there is a photogrammetric model with this is the seismograph of the cave because it's very close to a quarry and there are some explosions and they need to control because it can deteriorate the paintings, okay? And 9D is the security. Security means all the fire safety, all the safety analysis, the emergency response if you have one person that has a problem, a heart attack. All this information has to be here in security on all the elements that can help you, and all the instructions, all the evacuation plans, all the instruction for accidents, from injuries. Just the idea is to reduce the effect and to make it safe. Okay, this dimension has been inherited from the industrial models. Okay, thinking and industry, so the same. And the last one is the relation of the cave with the all the surrounding places that are near. So here you see the Altamira cave, the roots, you can model the roots. Here each point, it's one site of the same moment, okay? Paleolithic sites and newer sites. And here you can model all the natural paths they follow to move from one site to another. This information has been used to create probability maps to find new places. In 2 counties of Spain, we have found, following this and to elaborating one probability maps, we gave to the local archaeologists, and when they went to our work near, they visited the area we had with highest probability, and they have find 7 new sites with rock art in one place and 5 in another county. Okay, so here in Spain there are still a lot of places new to find. This is one area. Look, this is a river and with many shelters. So you can use the 3D model made with drone and to put all the site information. Just this model was used 15 years ago to create a Kinect flights. The Kinect was a tool for video games that you can put like a bird and navigate it by flying. So this was exposed in a museum with a Kinect. The Kinect was a tool for the Xbox, the first Xbox. It's a bit old, but it was the way of navigating the model. Okay, you put all the sites and later you have detail on some parts. And this is the context nowadays with Google Maps, so you can take all the information from Google Maps to overlay with the model, because if you need it to find potential problems with accesses, because here in Monte Castillo they have one problem, because one person in Las Monedas has a heart attack. They have to take out of the cave, but the ambulance could not reach the door of the cave, and the cave is around 700 meters from the reception center. So the path, the road was not wide enough to an ambulance to come to the cave. So they have to move the person 500 meters between the people, or 600 meters, just to reach the place where the ambulance was. So this is very important when you have caves open to the public, okay? All the access, all the logistics needed, and this risk of open places, because these places are living laboratories. If one person gets sick, and throws all, there's a lot of bacteria and problems. You have to clean it very well. So finally, these are the 10 dimensions I pretend to show you, and how we store them, and how we take advantage of geomatics and other techniques surrounding to create these digital twins of digital heritage caves, okay? Or cultural heritage caves, digital twins. So basically, we call it RACIM, rock art, okay, information modeling, cave management. These are the advantages. Basically, it increases the sustainability of heritage. It can improve the management, the conservation, and all the planning tasks. It helps in the conservation and the protection of the environment. It facilitates all the research. Now, these 3D photogrammetric models are used by researchers to reassess the art. It makes easier the dissemination of these cultural heritage places. It's good for security, and the operational efficiency is good. So if you are interested, this is, like the model, okay? You have the 3D model, you have the photogrammetric model, the GPR model, the UAV model, and below you can put it in physics simulations software and to calculate, okay? So if you are interested, you can see more details, or you can get more information in cuevasdigitales.com. That is our way. I apologize that it's in Spanish, but I know that most of you can speak Spanish, Sandra. So thank you very much to all of you, and I hope you enjoy the communication and learn a bit about the caves, geomatics, and digital twins. Thank you very much.
So thank you.
Thank you.
Thank you for your talk. Thank you for your great work. So important for humanity and for future generations. So maybe some have questions.
Yes, can I ask a question? So to be the first, it's a good variant to open our maybe short discussion. But so Vicente, I'm once again impressed by the work that had already been done. So it's fantastic. So and thank you a lot for your report, because so once again I see a lot very interesting thing. And so my question is, so you have a lot of data. You have a lot of 3D models, ortho plans, so point clouds, and so on and so on and so on. And one of the most important problem is the storage, keeping the information. So could you so maybe explain, and maybe in 1, 2, 3 points, explain what are the best platforms for keeping this information and demonstrating this information, and how you're solving this problem, because it's not easy to demonstrate this huge 3D model and so on. Please solve.
Yeah. Okay, thank you for the question, Vasily. It's a problem because to have an idea, the last, I didn't show, but the last photogrammetric model of Altamira was a 3D model with 200 microns resolution of the whole cave. It's about 400 meters. So only the pictures, we took the pictures, the revelated pictures, where it's around 15 teras, okay?
Oh,
So in Altamira, yes, we took 85,000 pictures, okay? For the whole cave, not polychrome sailing because we had from a previous campaign. So this is the rest of the cave. So in Altamira, we have around 40 teras. So here storage is very important. So in the last, now we are working on it now. We have to distinguish between levels because there is some information you don't need to have available in your storage, but you need to have access if you need, for instance, pictures. Not all the pictures of the 85,000 pictures need to be accessed every time, every moment. But some of the information, yes, because you need information, real-time information of all the sensors, climate sensors. You need information of these 3D models, photogrammetric 3D models. We have cut and create some low resolution models. And if you have 40 terabytes of information, maybe with 4, 5, 6, 8 terabytes is enough to store the information. The people from the museum need access from time to time, okay? So what's the way? Now there are two ways, or the cloud or a NAS, a local NAS or Dropbox, all these clouds. These are in the way we are working, okay? So they have some Dropbox and they have a NAS as well, and extern hard disk because it's a lot of information for a cloud service. It's very expensive and it's not. The idea of this is just to be useful and cheap because if it's not cheap, you can spend it 1, 2, 3 years, but no for forever.
Mhm. Okay, thank you. So the same problems. And well, the second question is about artificial intelligence. So do you have any idea to use it for, I don't know, understanding the prospecting of the caves, I don't know, for images? Maybe you have the real experience, or maybe you're thinking about it. So your ideas.
Artificial intelligence, I think, is a mix between fog and utility. Okay. I think it's a bit fog because here we are a bit in a early layer, in an early moment. Okay. We in archaeology, we don't used to have many examples to train systems in artificial intelligence. We can use artificial intelligence in preventive conservation. We have because you have a lot of living data. So if you can georeference sensors and use these algorithms or these bog tie, systems of artificial intelligence, they can predict you if you are going to have a problem or not. But here the problem is not to say, okay, you are going to have a dew point, okay, in the painting. But the problem that artificial intelligence has not reached, still not reached, is where. Because, okay, I know the conditions. Now it's a very high probability moment of this dew point. But where? In which part of this sailing is going to be the problem? So you need a lot of sensors and a lot of information. So it's a bit early. We are start using it for hyperspectral remote sensing, just to see patterns of pigments with these methods, but not too much. And I know some scientists are using to create real-time cartographies, but in cave is not so relevant because it's not a very dynamic place. So the cave is the same for years, maybe. So this live cartography is not useful for caves.
Okay, thank you a lot. Thank you for your report. So I have no more questions. Maybe some other persons need me. I don't know, Sandra, or maybe.
Okay, thank you very much. Thank you very much, Vicente. Great presentation, and the results are astonishing. So, more or less to judge, how long it took to from the start of the project to arrive to the contemporary condition. So, like, I don't know, about a decade or some years, or it was very fast. But judging from the amount of the work, it seems that it was not so fast.
We started working in Altamira in 2012, 2013. So it's a project that is continuous growing. So once we reach one stage, we start working in the other. So we have finished now. We have some GR campaigns, you know, for monitoring biodeterioration, humidity, these critical areas, and some others that are punctual. You know, we finished the 3D photogrammetric model of the cave, so maybe we will not continue doing any more photogrammetry, maybe in tens or even more years. So in this case it's a living project. In other caves that they only need, you know, the 3D model or photogrammetric model, they used to be one photogrammetric model was 1 month, 2 months. It depends on the resolution and extension. But if you are going to integrate GPR is costly as well. 1 month, 2 months, and it depends the problem. We used to work. Sites has a problem, and we all together try to see which is the best way to solve that problem. It's conservation. You need to document art. Geology is an issue because you have some feelings. Where are the feelings? You know, GPR is the purpose is another. Or if you have a focus of and you know biodeterioration or contaminated soils, or so just to try to prevent the problem to be bigger. So it depends on the project. It could be weeks, years, or or decades.
Gracias.
Thank you.
Okay. Коллеги в Zoom, может быть, кто-то хочет еще задать вопрос?
Нет, Елена Сергеевна, никаких вопросов нету.
So, I think that's all. Thank you one more time for this presentation.
Thank you very much, Vicente. I hope
Thank you.
So we in contact.
Thank you, Vasily. Thank you.
See you later. Thank you a lot for your reports one more time.
Okay.
Thank
you to all, and thank you to Centro de Estudios Mayas, and thank you very much for the invitation. It was an honor for me.
And if you have something more, or maybe your colleagues would like to present something about, so I don't know, any projects, or not only about caves, so where I think Dmitry also can say that we are glad to meet online and to hear and to discuss all your projects.
Yes, of course. We have many places. We have, you know, castles in Bahrain.
It will be very interesting. So we are open to communication. So every time. So
okay, even Maya. We have
Batum.
We have some places, interesting places.
Thank you a lot. Gracias.
Thank you very much.
Muchas gracias y muy interesantes. Estamos en contacto. Un placer.
Gracias. Buenas tardes.
Все, Сандра Гимс, завершаем?
Да, все, завершаем.